So basically, when you're doing a complex circuit, especially one that has holes in it, all right, it's not, they didn't give you all the resistors and they just want you to kind of find the total current or something. They have holes in it. And then it's a puzzle piece. We're going to approach it by looking first using Kirchhoff's law to fill in what we can fill in, laws and rules, and then we're going to use Ohm's law to do whatever math we can. And then we kind of go back and forth until we filled up everything we can. So let's go ahead and let's start with, I'm going to start with current only because they gave us the full amount of current at the top. Okay, so Kirchhoff's junction rule basically says that current in equals current out. So I'm looking for, if this was our current into the system, what has the full current out of the system? R6. So that means R6 has to have that full amount of current because that's where it all joins back up. Okay, so there's R6. Now the next current they give us is R5. And amp. Now if current in is equal to current out, okay, in this case we know that the out was 2 amps and one path was 1, then by definition we can kind of figure out what that is, right? Literally 1 plus 1 is 2. So that becomes, this is 1 amp. Okay, and we can use the same logic on R3. If R3 had a current of 1.5 amps, then that same idea, current in equals current out, what plus 1.5 is equal to 2? 0.5. So we have two things here, right? So the question becomes, is it going to be the same current over both of those? What do you think? Yes. Can you think of why? It's in a line, right? Yeah. The current only changes when the path changes. So up here, there's no change in the path, so therefore it has to be the same current over both of those guys. So there's 0.5 and there's 0.5. All right, so that covers that. I'm going to clear off my screen just a little bit here because it's kind of messy. All sorts of buttons I got to hit sometimes. Okay, so that covers that bit. All right, so we have managed to get everything taken care of on current. Now we're going to look at voltage. Voltage, Kirchhoff's voltage loop rule says that the voltage around a closed loop must equal, the sum of the voltages must equal 0. So if R4 here, looking at this one first, if R4, if the voltage across this path right here is 4 volts, then that tells us that it must be the same as the voltage drop across R5. Because whenever the voltage comes in from here to here, there's nothing changing it. It's just wire. So that means there is no voltage change across the wire. So that means that the 4 volts across R4 will be the same as the 4 volts across R5. Next, I'm going to look at R2. That's our next voltage. And honestly, I can't do anything with that in Kirchhoff's loop law. And I can't do anything because I don't know what R1 is. And unless I know what R1 is, I can't figure out what R3 is. Okay, does that make sense? All right. So I've gone as far as I can using just Kirchhoff's loop and junction rules. Now I'm going to try to use Ohm's law and do whatever math that I can. So for example, I can do 0.5 times 5 is 2.5 volts. I can do 2 times 2 amps on R6 is 4 amps. And then I can solve for the resistance using voltage over current. So the resistance across R2 is 3.5 divided by 0.5, or it's 7 ohms. And the resistance across R4 is 4 divided by 1. So it's 4 ohms. It's the same for the other one, R5. We've now cleared everything that we can. And here we have that little R3 that's just stuck there waiting for information. But now I have some more. I know that in addition to knowing that this is R2 is 3.5 volts, I know that R1 is 2.5 volts, which means that the total voltage drop, okay, across this path, R1, R2, is 6 volts. So if that voltage drop is 6 volts, now we go back to Kirchhoff, right? So if the voltage drop across one path is 6 volts, it's going to have to be a voltage drop of 6 volts across the other one. Okay? And because there's nothing in there changing the voltage once it splits. Right? It doesn't split. So it doesn't change until after the split. So 6 volts divided by 1.5 is 4 ohms. Okay, now we are going to use a couple different ways to fill in the 2 boxes at the top. For the resistance, we're going to treat it like equivalent resistance, just so we get practice doing equivalent resistance on something big and ugly. Okay? So, and the thing with doing equivalent resistance over something this big is you're going to see that I'm going to redraw it. Every time I simplify it, I'm going to redraw it. Because if you hold it in your head, it's just, your brain can do all the pieces, but it has a hard time holding it. So, what do we got? We have got 5 ohms, 7 ohms. I'm just going to fill in my resistors so we can see them. 4 ohms, 4 ohms, 4 ohms, and 4 ohms. Okay, so it's a nested thing, and you go down to the smallest piece of the nesting, and that would be that R1 and R2 are tucked inside of this one. These two are tucked together, all right, and then at the end, I've got the entire thing as a series circuit. So the smallest tuck is that yellow one, the R1 and the R2. So I'm going to simplify that first. So that becomes, and I'm going to redraw as I go, that becomes 12 ohms up top. The 4 on the bottom hasn't changed. And then over here hasn't changed. Okay. And then, so these are 4 ohms, and 4 ohms, and 2 ohms. All right, so I just got to do the equivalent resistance of the others. So I'll do it in blue over here on the side. So 1 over 12 plus 1 over 4 becomes 1 over 12 plus 3 over 12, which gives us 4/12, which is 1/3. And you take that inverse of that last sum, right? So that means that that becomes 3 ohms. And then if I do the 4 and the 4, well, 1/4 plus 1/4 is 2/4, which is 1/2. There's your last inverse. 4s, 12s, and 6s work really well for kind of being able to do them quicker without a calculator, just as a heads up. Other numbers you probably need to do calculator, but these are designed for quick numbers. So there's that. There's 2 ohms. And then here's the final 2 ohms. And now all I have to do is do the R in series, resistance in series, which is just add them up. 3 plus 2 plus 2. So our total resistance is 7 ohms. So because of Ohm's law, we could go ahead and just use the current times resistance, and we can get 14, and we know that's what it's going to be. But I also want us to get practice trying to pull the numbers from the circuit itself. So we're going to keep that 14 in the back of our head, and we're going to use the voltage drops to tell us what the total voltage is. I'm going to clear the screen really quick. So if we're going to do that voltage drop across there, the one we know, ooh, that was the wrong variable. And nobody caught me on that one this time. This should be 4 volts, and this is 4 volts. So the voltage drop across R6 is 4 volts. And on R4 and R5, from point to point, it's the same voltage drop, right? So this voltage drop is, according to our table, 4 volts. And so I come up and I look at the next one, and well, R3 is 6 volts. And if I look at this, this is 2.5. This is 3.5. So of course, this top voltage drop is 6 volts. So no matter what we have, so we have a 6 drop voltage, we have a 4 drop voltage, and a 4 volt drop. So 6 plus 4 is 14. So we just kind of did that 2 different ways. And that's kind of how you work the complex circuit. Again, you use Kirchhoff's junction and loop as far as you can go, and then use ohms. And then start, okay, where else can I use Kirchhoff's junction? You kind of, depending on how, you're not going to have to do ones that are this hard, actually. But this is where we're practicing, because that's so you get the most out of it. So, yeah, so just go back and forth between Kirchhoff and ohms, and you'll be fine.